Okay, so how's everybody doing? How's how's your first semester in your first year of studying computer science or studying whatever it is you're studying going? Yeah? Do you find it hard? Um,
Writing some of my other courses, but
yeah. So, but overall, just as a collection of whatever, 4 or 5 courses at once, how's the workload? Decent?
I should complain. I have 15 hours of classes a week.
Yeah. And the workload's not impossible? Okay, good. Good that the class is shifting this way. That's where the screen is. So we're done, or I'm done teaching you about Pygame. What you learn about Pygame after this is completely up to you. Explore it yourself. Figure out what you need to do your what it is you want to accomplish with it. But now it's time to move on to another topic in this course, and this is a topic that's near and dear to me. It's really algorithms and problem solving. Algorithms is my general area of research, and it's really a topic that's at the core of almost everything we do in computing. You may not have thought of it this way, but for many of these assignments, you have been coming up with algorithms. So before we get too much into discussing algorithms and exactly what they are, in order to really be able to do a few things, define some algorithms and also to analyze other algorithms, we need to make sure that everybody is on the same page with respect to recursion. So recursion is just what happens when you have a function which calls itself. Or maybe it calls another function which then calls it back, which is just another way of calling itself indirectly. So let's look at an example of that. Today is November 8th. Okay, so we'll define a function called printer. It'll take a single, let's say, integer argument n, and it'll print n, and it'll call printer of n minus 1. So, this is a good function. So what will it do? Yeah, so let's see that. Yeah, so if I do printer of 10, bunch of stuff goes by. We scroll up to the top. The error message is so long it takes up about 1,000 lines by itself. And here's where we called it. It printed 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, minus 1, minus 2, minus 3. Went for a long way, all the way down to nearly 1,000, 988, and then it crashed. And then it prints a super long message that shows you all the function calls that were executing at the time the crash happened, and there were 998 of those function calls. Yeah, so 998, and so that's what it's showing you. They were all executing line 4. Line 4 is that line there. They were all calling this thing recursively, right up until the end there. when it tells us that the maximum recursion depth is exceeded. Okay. So the first thing you need to know about recursive functions is that they have to have a mechanism to stop themselves. So if you just have a function which all it does is call itself, well, when it calls itself, it's going to call itself again and again and again and so on. So you need a mechanism to stop it. And so in mathematics, that's called a base case. Sometimes in recursion, it's called a base case or termination condition. Call it whatever you want, but you need to have some executions of this function where it doesn't call itself. And in this case, maybe we want to do something like only count down to 0, so if n is less than 0, then all we'll do is return without doing anything else. Okay. And now if I call printer of 10, it counts from 10 down to 0. Now, this error message that we got said maximum recursion depth exceeded. So the question is, I guess one question is, well, why did we get this error? Why? I mean, we wrote an infinite, what we wrote was essentially an infinite loop. Why didn't it just loop infinitely? Right, we could redefine printer a different way to say, while 1 is less than 2, print n equals n minus 1. And that function, it has no problem counting down past 988 or minus 988. It'll just keep going forever. So why did this recursive one, when we left out this base case here, why couldn't it count down forever?
Python have a limit to how many times you can do recursion?
In fact, every language has a limit to how many times you can do recursion because of what recursion does. So,
is it only limited to that specific function or the entire program in general?
Generally, it's all the functions that are called at any given time. So, so what we should look at is really what happens when we call this printer of n function. And for that, we want to understand what's called the runtime stack. So you may have noticed that, or hopefully you've seen, understood something like this, that when we pass arguments to functions, or when we define variables inside of functions, you get to use them while you're in the function, but once the function is done executing, those things are gone. So let's just do a silly example of that. And we can say a equals x, print a. And now if I call my fun of 10, it prints 10. Now notice my fun assigns x to a. X was 10. So if I ask what a is, it says it's not defined. And that's because the variables that are defined inside of a function like this, they're only defined while that function is running. At this point, the function has stopped running. It printed a and returned, so it's done running. So they're not available. In the same way that x, the argument that we pass to that function, is also not available anymore.
Are they considered local variables? Because I know some languages.
These are what's called local variables, meaning they're local to the function.
I just didn't know if it was the same with Python.
Yeah. So how does all this happen? Why do these variables appear and then go away? Well, when you call a function, like for example, when I call my fun, there's this thing called the runtime stack that you can think of a little bit like a stack of plates, where each function call is a plate. And so when I call a function, you start out with, let's just call this thing here the empty stack. When I call my fun of x, this pushes onto the stack a new thing called a stack frame. And that stack frame contains variables which represent the arguments that are in that function, to that function. So in this case, there's a variable called x. Remember, variables, we draw them as little boxes. And x is, when we call this thing, x gets the number 10. And when we define a new variable inside that function, that variable goes into this stack frame. So in this case, we get another variable called a, which also gets the number 10. And the function executes, and when it needs to look up a variable, or when it needs to know the value of a variable or change the value of a variable, it starts looking here in this stack frame. And maybe it doesn't find the value of a variable there. It might look up in another stack frame higher up. In this case, there's only one other thing. It's this global stack frame. So if you access any variable that's not x or a, it had better be a global variable that's available. And then once the function's done executing, it returns, and this whole stack frame gets wiped off the stack. Just disappears entirely. Okay. So, so what does that mean for a function like printer here? Well, printer, when we call it with the value 10, it does exactly the same thing. It makes a stack frame. That stack frame has one variable inside it initially, which is n, and it gets assigned the value 10. Okay. So now printer starts executing. It checks if n is less than 0. In this case, it's not. It then prints the value of n. And when it needs to know the value of n, it just looks it up here. And then it calls printer of n minus 1. So in this case, it's printer of 9. And, well, what does that do? Well, that executes exactly the same way. It adds a new stack frame. That new stack frame has its little own variable called n. And that variable is assigned the value 9. It prints the value 9, and then calls printer of n minus 1. 9 minus 1 is 8. So that creates a new stack frame with this thing called n, and this variable 8. And this thing really is a stack. You can think of these things as being piled one on top of the other. This stack frame up here doesn't go away. The stack frame with n equals 10 doesn't go away when we call this with 9. It's still there. The stack frame with n equals 9 doesn't go away when n equals 8. And by the time this thing gets down to, if we leave out the base case, this thing gets down to n being assigned the value minus 988. Python says, wait a minute, there's something fishy going on here. This thing is getting huge, and I'm actually required to remember all of this, and this is getting too big to keep track of. Python limits the size of the stack to be to be about 1,000 frames. So it just says, okay, there's something wrong here. I'm not willing to continue. This is probably a programmer error, probably an infinite loop. If it does continue, if it allowed this to continue indefinitely, then there's a good chance that this would just soak up all the memory in your computer, which is usually not good, because when that happens, your computer then starts to look for memory elsewhere. In particular, it starts to look on the hard disk, and then everything gets extremely slow, and it becomes difficult to even stop this program from running at that point. So what happens is your computer essentially becomes unresponsive. Okay. So by putting in this base case, well, we stop this early, and instead of going all the way down to minus 998, we get to a state where n is 0. Then, well, this still isn't true, so we print n, and now we call printer of n minus 1. So in this state, we have n, it's minus 1. Minus 1 is less than 0, so what we do is immediately return. And what does returning do? Well, it wipes off this, this stack frame, so it just deletes it. And brings us back up into this stack frame. And we're still executing at this point the code from printer. In fact, we have just returned from this function call right here. So if there's more code after this, now is the time that it will get executed. In this case, there's nothing. The only thing that comes after this is an implied return statement. So then this stack frame gets wiped off, and the next one gets wiped off, and the next one gets wiped off, and so on. And eventually this finishes when this last function up here returns. Okay. So is that clear? Yep.
What ends up being the return statement?
Nothing gets returned from this. So if you in Python, if you don't have a return, or you have an empty return like this, the value that comes back is none. So what was it? Printer 10. If I say q equals printer 10, no, this is the old version of it. Q is just none. Yep. That's a good question. So here we've written this recursive function that prints these numbers, and well, you know, what if we say, so this function is correct now, it does stop at 0, but if we call printer of 5,000, we'll still get this crash. And we can see how far it got before it crashed. I think what we should do is open a new terminal. And how far did this get before it crashed? It got nearly down to 4,000. Yep.
I'm kind of confused. If the stack frame that gets returned just wipes itself out and it goes up to the previous stack frame.
Yep.
Why doesn't where n is now 0?
Yep.
Why doesn't it go and try to?
Well, no, it doesn't go up to the previous. So you're wondering where it executes from that point onwards when it returns. Okay. So here's the question for you. What happens if I change the location of this print statement and I put it here? So what will get printed then? Yeah. What's that? Well, what happens if I call this with n equals 10 or something? What numbers will I see? So I'll see 9 to negative 1, because if I call it with 10, I will never print anything Well, no, not even that. I mean, if I call it with 10, then I'll eventually I'll print 10, right? So it will print 1 through 10, or sorry, 0 through 10, just like before. Yeah.
Would it put them in reverse order?
Yeah. So before, this thing was a function that counted backwards from 10 down to 0. Now it's a function that counts from 0 to 10. So why is that? Well, if we look at this stack frame picture, we start out with the first call to this function creates this stack frame with n equals 10. And then the next thing it does immediately after that is to make a recursive call. It doesn't print anything yet. So it makes a recursive call with n equals 9, which then also immediately makes a recursive call, and even n equals 0 makes a recursive call, so we get the stack frame with n equal to minus 1. Now this is where n is less than 0, so this thing just immediately returns without printing anything. So that's why we didn't see minus 1 in our output. And it returns back to this stack frame, and the execution for this function resumes where it left off when it made that call. Right? So where did it make this call? That was in this line. So the next thing that happens is the next line of code here, which says I should print n. What's the value of n? It's 0. So it prints n, then the function is over, it returns, so it wipes off this stack frame and takes you back up to the stack frame where n equals 1. And that prints 1, and then takes you back up to the stack frame where n equals 2, that prints 2, and so on, all the way back up to the stack frame where n equals 10, which prints 10 and finally returns. Okay. Is that clear? Good. And so then what if I print n in both places? What gets printed? Yeah. Yeah. So this will count down to 0 and then count back up to 10. And again, we can see that from this picture. The first thing that happens is this thing comes with a stack frame with n equals 10. It then immediately prints the value of n, which is 10, and then calls printer of n minus 1, which creates a stack frame with n equals 9, which immediately prints the value of n, which is 9, and which creates another stack frame with n equals 8, which immediately prints 8, all the way down to minus 1. And then on the way back up, as it returns, each stack frame starts executing right after this line here, which means that it's going to print its value of n again, but this time they're coming out in the other order. So every number should be printed twice. We can just check that. Let's just do 5. So 5, 4, 3, 2, 1, 0, 0, 1, 2, 3, 4, 5. Okay. All right. So we're good there. Good. So then it's a little bit clearer now, maybe. So your question, someone's question was, well, shouldn't we check if n is less than 1,000 so this thing doesn't crash? Yeah, if we were worried about that, we should make some kind of checking to make sure it doesn't crash, or we should wrap the whole thing in a try-catch or try-except statement to handle the crash gracefully if it does happen. The problem with checking if n is equal to 1,000 or is less than 1,000 is the maximum size of the stack varies from system to system. And so that might work for this version of Python, which is running on my machine, but 1,000 might be smaller than necessary for the version that's running on your machine. And so basically the general rule is any implementation will give you a reasonable sized stack. If you try and make it unreasonably big, you can expect that there may be a crash. And if you want to know, exactly how big you can go, or you're pushing those limits, just put a try and accept around that piece of code that may cause this to happen, and then you can gracefully recover from it. Just like we recover from input errors and data conversion errors and so on. Okay, so the factorial function you now know. How would I write that recursively?
Is it just meant to return the factorial?
Yeah, so 1 times 2 times 3 times 4 times 5 all the way up to n. Yep.
So you say return n.
Yep.
Multiplied by factorial. But you need to have a base case.
Yep. So this is actually the way I program all the time. I write the recursive part, and then if I'm lucky, I remember the base case. And what's the base case here? Sometimes.
If n is equal to 0, or if n is equal to 1, return 1. And that's 1.
So if you look up the formal definition of factorial in a textbook, in a math textbook, you'll find that actually it's 1 for both 0 and 1. So factorial of 0 is 1, and factorial of 1 is 1. And then if you think about, okay, what happens if I compute factorial of n, or factorial of 1, then I'll get 1 times factorial of 0, which is 1. So it all just works out that way. Okay, so there's the factorial function written as a recursive function. And this is pretty good as long as you only give it an integer argument that is bigger than or equal to 0. If you give it a negative number, there's going to be some issues still. Okay. Any questions so far? Okay. So here's an exercise for you. I give you a list, A, and I would like you to write a recursive function that adds up all the numbers in A. I know that you don't need recursion for this. There's many easier ways to do this. But how would you write such a function? Yep.
Did you say you're giving us a list A?
Yeah.
Okay.
Yep.
So the base case would be if len A is equal to 0, or if len A is equal to 1.
What's the sum of the numbers in elements in A if it's equal to 0? If the len is 0. So always go with, try and find the simplest base case you can. Sometimes you may need more than one base case, but in this case, if the length of A is 0, then you add up nothing, you get 0. So we'll stick with that.
You say return
Yeah.
A 0
Yep.
plus somewhere A, then you just slice from the 1 to the n.
Okay. So these recursive functions are almost always based on a mathematical principle called induction, which you'll learn about when you take discrete math. But the idea is basically to solve a problem, and usually there's some notion of the size of the problem. So for example, the size of the factorial problem is the value of n. So if I know how to solve it for a small value, n equals 0 in this case, and I know how to make a big value smaller, then I basically have a solution that's recursive in this way, right? So for factorial, I know how to solve it for n equals 0 because I know the answer. The 0 factorial is 1. And if you give me something bigger than 0, I know how to make it smaller because I know that I can get factorial of n by multiplying factorial of n minus 1 times n. So the thing that gets smaller here is the value of n. For this summing the array problem, the thing that's easy to handle is when you give me an empty array, it's really easy for me to sum up the elements. I can just tell you that the sum is 0. And if you give me an array which is bigger than that, then I'll take the first element and add it to the sum of the rest of the elements. So that's what I'm doing here. And this will work because this recursive call is on a smaller array. It's an array. If the original array had length n, then this recursive call is on an array of length n minus 1. And this can be really powerful, this kind of thing. So let's do a quick test of that. A is equal to range of 10. What should the answer be? Quick. Too slow. 45. And we can check because Python has a built-in sum function which does this for us, making the whole exercise completely pointless, except as a way to help us understand recursion a little bit better. Now, similar issue applies here. If I take A to be a range 10,000, then the built-in Python function has no problem computing the sum of that. What's going to happen with our function? It'll crash. And it'll crash because the way it's going to compute the sum of this array of length 10,000 is it's going to set up a stack frame with an array of length 10,000, and then another stack frame with an array of length 9,999, and then another one with length 9,998, and so on, all the way down to about 9,002 or so, and that's when it's going to crash. So there we get this error that the recursion depth was exceeded. Okay. So that's an issue. This recursion depth is limiting sometimes, but sometimes there's ways we can get around that. Now, if we look at this function, is there any other ways we maybe could have written it that if we give it a big array, it might not have such a big recursion depth? So you're saying if I have a list of 10 numbers, the way I add them up is I take the first number and then I add up the remaining 9 numbers. So is there another way of adding up a list of 10 numbers? Not, I mean, still recursively like this, still defined recursively, but maybe just a different ordering. Yeah? Not, it doesn't have to be a different order, but just a different way of doing it. No, that will still only take off one element, and then we'll recurse on 9 elements, 8, and so on, which isn't going to work if we have more than 1,000. Yeah?
You could add up the first half and then add up the second half.
Yeah. So another way to do, to add up 10 numbers is to add up the first 5 numbers, and then add up the second 5 numbers, and then add those two things together. Okay? So let's see if we can implement that recursively. So now we need to be a little bit more careful. And we will go with a couple of so now we've assured ourselves that the length of A is bigger than or equal to 1. And so the idea is, well, now we can add up A by adding up the first half of the numbers and then adding up the second half of the numbers. So how do I get the sum of the first half of the numbers? Yeah. So 0 up to the len of A divided by 2. And that'll work for us. That'll give us something because we know that the length of the array is at least 2. It's not 0 and it's not 1, so it's at least 2. So even when we divide by 2, there'll be something there to add up. And well, what we want to do is add that up. So that's the sum of the first half of the array. And then we want to add to that the sum of the second half, which starts at position len of A divided by 2. And maybe just to tidy things up, we'll just call that M for the midpoint. This is a nice thing about slices in Python. Is they include the starting endpoint, but not the final endpoint. So if I use M as the end for the first slice, that means it won't include that index M. And if I use it at the beginning for the second slice, it means it will include it. So it's exactly a perfect partition. We're not counting anything twice here. So yep. That's okay. Shall we try it? Do we think this is going to work?
No.
No? Why?
Because you haven't mentioned the addition in summer 2.
Well, this is summer 2.
Yeah, you haven't implemented any addition.
Yes, there's addition right there. Yep.
And they're just going to add and then redivide, redivide, blah, blah, blah.
Well, it's going to add up an array A, it's going to add up the first half, and then it's going to add up the second half, and then it's going to add those two things together.
But when it calls, okay, let's say it goes down to return summer 2A, the first slice.
Yep.
The first slice, it's just going to pass the array from 0 to the first place you sliced.
Mm-hmm.
And it's going to do all that checking, and it's going to return the same thing.
Let's find out.
It doesn't add it up.
Let's find out.
I feel like it is.
It returns that same array.
So what was A is range 10? We know the answer for that. It's 45, right? So the real sum of A is 45. The summer of A, which is the original version we wrote, gives us 45. And what about summer 2? It also gives us 45. And here's something interesting. Let's make A be an array of length 5,000. So then the sum of A is this big number here. The summer of A, we don't know because it crashes. And the summer 2 of A works. So, anybody know why? Yeah. 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 So the way to see it, if you don't know about logarithms and everything else, you do now know about recursion depth. And so we know that if we call summer on an array of length 10, we basically get a picture that looks like this, except instead of n, what we have is a bunch of a's. And these a's are arrays, and these are the lengths of those arrays rather than the integer that's stored there. Now, in summer 2, starts out the same way. We get an array A, and the length of A is 10. So I'll just write this way, even though it's not, because I don't want to have to create an array of length 10. Now, summer 2 then calls this. Well, so let's see what it calls. The length is not 0, it's 10. The length is not 1, it's 10. So it computes the length of A over 2, which is 5. And then it calls summer 2 on the first 5 elements. Okay. And so maybe the better way to write this down is to say A contains 0 up to 9. Now it calls summer 2 with the first 5 elements of that array. So that means A contains 0 up to 4. Now this starts executing, and it calls summer 2 on the first half of that array, which is only 2 elements. So that's A, which contains 0 and 1. That calls it again, and now A contains only 0. And when A contains only 0, its length is 1, so all we do is return that value. Okay. So this is done executing. We'll put a little X here, but I'd like to keep it here just in the picture rather than erase it. This is done executing, and control now is back up in here in this function, which is calling it on an array of length 2, and it's already called it once. It's already called it with the first half of the array, which was the 0, and now it's going to call it on the second half of the array, which is the 1. So this calls it with an array A, and this array A is only 1 element. It contains a 1. Well, that's an array with 1 element, so it just returns the value of that element, right? That's this line of code here. And so the return value that comes from there is 1. The return value that came from there is 0. So now it adds 0 and 1. That's this plus here, and returns the result. So the return value that comes out of this finishes, and it returns the value 1. Now this guy has called summer 2 on the first half of its array. Its array contains 0 through 4. Now it's going to call it on the second half, and the second half contains a 2, 3, and 4. Now this guy's going to call it on the first half, which contains only 2. Which is going to return right away, giving back the value 2. This function now has still only called it on the first half. It has to call it on the second half. I wish I had done 8 instead of 10. A has 3 and 4. It's going to call that on the first half A with 3, which is going to return the value 3. Then it's going to call it on the second half, where A is 4, which is going to return the value 4. This thing is going to add those two return values together, 3 and 4, and then it's going to return that, giving 7. This thing is going to add its two return values together, 2 and 7, giving 9. This thing is going to add these together, giving 10. Okay? And then the whole thing is going to continue over here on the right-hand side with the values 5 through 9. Okay. I'm not going to draw the right-hand side because I'm out of space on my page, but indeed you can check that actually each of these things is returning the correct sum of the array that it was given, right? So this was given an array with one element that contains 0, so the sum of that is 0. This one was given an array with two elements that contained 0 and 1, and the sum of that is indeed 1. This was given 2, 3, and 4, and indeed the sum of 2, 3, and 4 is 9, and so on. And the sum of 0 through 4 is 10. And so this thing actually gives the correct result in the end. But notice here the recursion depth is not the same as it is over here. So in this thing, the recursion depth was 11. So we counted down from 10, an array of length 10, an array of length 9, an array of length 8, and so on. In this thing, well, the recursion went down from an array of length 10 to an array of length 5 to an array of length 2 to an array of length 1, and then stopped there. Then this stack frame disappeared before this stack frame got put on, and so at this point the recursion depth is the same for both of those things. It's just 1, 2, 1, 2, 3, 4. And actually, if you looked at this whole recursion tree, you'd see that we never got below 5. These are the deepest guys here. Here you have 1, 2, 3, 4, 5 stack frames on the stack. Okay. So the difference between 5 and 10 is not huge, but the difference between 5,000, which is what you get when you call this on an array of length 5,000, and what happens there is, well, the number of stack frames is however long it takes you to get down to 1 when you start dividing 5,000 by 2. Okay. And if you remember, or maybe you don't remember, maybe you never learned about these, that's just the base 2 logarithm of 5,000. Okay. And logarithms grow very, very, very slowly. So the base 2 logarithm of 5,000 is it's less than the logarithm of 8,000, so 10, 11, 12, it's about 13. So for 5,000 elements, you get about 13 stack frames. Using summer 2, you get a recursion depth of 13, and you get a recursion depth of 5,000 using summer 1. So that's why summer 1, the original summer, crashes. Summer 2 can work for really, really big, really big arrays. Yeah. So what do you mean by large stack or smaller stacks? Well, there's no different stacks. There's only one stack. So if I wanted to do this picture properly, looking like it was running in real time, then this picture would have been a stack with this thing, this thing, this thing, this thing, and then I would erase this piece here. So I don't know how to hide that. So I would erase this piece so that the recursion stack only has 3 things. This gets popped off the stack, and now this comes on, and now there's only 4 things. So the stack really only ever has 4 things, or when we get down to here, it has 5 things on it, but never more than 5.
Use slowest, largest possible stack.
It's only as it only ever gets as big as the longest path from the top down to the deepest thing there. So in this case, it only never ever has 5 stack frames on it. Yep. Nope. It's not, or most implementations are not. So so that's the point I'm going to make next is don't use recursion if it's not serving a useful purpose, because if you take a course in functional programming, for example, they'll want you to do everything via recursion, but functional programming languages know how to optimize for tail recursion, and they even know how to optimize for non-tail recursion in many cases. We don't get that with Python, so when you try and do things like, say, add up an array by taking the first element and then recursively adding up the rest, you'll get a crash a lot. Okay. So none of these are great examples of uses of recursion, because all of these we could do without recursion at all, right? These are all iterative loops. This is perhaps the best example, but it's not an example that we really need. Here's one that I want to show you. Has anybody heard of the quicksort algorithm before? Yeah. So the quicksort algorithm takes a list or an array of numbers and sorts it. So does anybody remember how it works? Yep. Yeah. So so you pick a random element from this list that you're trying to sort. We'll call it A. And then you split it. So for example, don't want that. So let's say I give you the numbers 7 to 0, 1, 6, 5, 3, and 4. So let's say this is the list of numbers that you want to sort. Then you pick one at random. So I don't know, maybe you get lucky or unlucky, and you pick 6. And now you actually partition these numbers into 3 different sets. So one set is the set of stuff that's smaller than 6. So over in that set is 0, 1, 2, 3, and 4. Another set is the stuff that's equal to 6. In this case, 6 is the only thing that's equal to 6, so it's there. And then you have another set, which is the stuff bigger than 6, which in this case, there's only one thing bigger than 6. It's 7. I forgot 5. Yeah, there it is. Goes somewhere over on this side. Okay? And you lay them out in that order. The stuff that's smaller, the stuff that's equal, and the stuff that's bigger. So that's kind of like sorted, right? There's the smaller stuff, there's 6, and then there's the bigger stuff. The only thing you have left to do now is to make sure this part is sorted, and then to make sure this part is sorted. If If you do that, then you're done, right? So that sounds exactly like recursion, right? That's what we want. We're trying to sort a big thing. We take a random thing, we break it into different parts. We should be careful and make sure that the parts we're trying to sort are smaller than they used to be. Otherwise, we could run into an infinite loop. If the way you sort A is you sort A, well, then you're in trouble, because then the way you sort that is you sort, and so on. But indeed, these two parts both have to be smaller because neither of them includes 6, this number that we picked. So they have to be smaller at least by 1 than the original thing. So we sort those. Now, let's look at that in Python. Well, and then there's a base case. So what kind of array is really easy to sort? Yeah, so if len of A is equal to 0, then we can either return A or the empty list. It's the same thing. A is the empty list. Otherwise, we make a random choice from A. And what we want to return is all the elements y for y in A if y is less than x. So this is all the stuff that's smaller than 6. We want to return y for y in A if y is equal to x. So that's all the stuff that's equal to 6. And we want to return y for y in A if y is bigger than x. So all of the stuff that's bigger than or equal to 6. Now, does this give us our sorted set yet? Well, we can try, see what happens. But what's missing still? Yeah, there's no recursion yet, right? All this is going to do is pick x, and maybe x is 6, and then it's going to give us back an array that looks, looks something like this. The first part is out of order, then 6 is actually in the right place, and then the second part is out of order. And we can just check that. So there's A. We call QS of A. I had it print out the pivot element. Pivot element it picked this time was 7. And it gives us 7 in that location. All the stuff that's smaller than 7, 7, and then all the stuff that's bigger than 7. But the stuff that's smaller than 7 isn't sorted. The stuff that's bigger than 7 got sorted by accident. It got sorted because it was 8 came before 9 in the input array. So all we need to do then is recursively sort the first part, the stuff that's smaller than x, and recursively sort the last part, the stuff that's bigger than x. The stuff that's equal to x is already sorted because it's all equal. There's no way to sort that the wrong way. So there's A, quick sort A, we get 0 through 9. Let's try something bigger. A is equal to range 10,000. Oh yeah. Now it's not sorted anymore. So if we look at the first 20 elements in A. They're not in any particular order. And if we say Q sort A, we didn't, we should stop printing things in our function. But it works regardless. So if I look at the first 50 elements of A sorted, there they are, 0 through 49. Look at the last 50 elements, there they are. So there is, this is actually one of the biggest selling points for me of Python, is that you can implement quicksort like this in what is basically 3 lines of code. There's not too many languages that you can do that cleanly. We'll come back to sorting algorithms a little bit later, probably next week. There's one other sort of a compelling application. So these things up here are bad use of recursion. This is not recursion. This is a bad use of recursion. This is a really bad use of recursion. This is a not so bad use of recursion, but still not great. And quicksort is really a good use of recursion. And if I gave you the task to write a program that sorts an array, the code that you would come up with would probably be more complicated than this, and almost surely not as efficient. Something I want to look at is another good use of recursion, which is something for computing what's called the power set. So if I give you a set of elements or a list of items, then the power set is the set of all subsets of that. And so power sets very quickly get out of hand. Let's just do a simple one. If the numbers, if the items that I give you are 1, 2, and 3, then the power set of this is a list or a set of sets that includes 1, 2, 3. It includes 1, well, let's do it this way. It includes 2, 3. It includes 1, 2. It includes 2. It includes 1, 3. It includes 3. And 1, 2, 3, 6. It includes 1 by itself, and it includes the set with nothing in it, which we write this way, the empty set. So this power set has a lot of elements. Even for 3 elements, there's 1, 2, 3, 4, 5, 6, 7, 8 things in this power set. So should be clear here. Each of these things is a set or a list, if you like. And so this power set or power list is a list of lists. And there's 8 of them for 3 elements. And in general, if there's n elements and items, then the power set has 2 to the n items. There's a really easy way to see that. If I'm looking at all the possible subsets of a collection of n things, well, for each thing I can decide whether it's in the set or whether it's not in the set. So it's like a light switch. It can be on or it can be off, or it's like a bit. It can be 0 or it can be 1. So really, a subset you can represent as this list of n bits that tells you for each element whether or not it's in the set, and any way of choosing those bits gives you a subset, a different subset, and so if you have n bits, you have 2 to the n different ways of choosing them. So let's see how we could do power set recursively. So we would like to get a somehow reduce it to well, I guess we can do the easy thing first, which is figuring out the base cases. So what's an easy case? The empty set. So if len of A is 0, then what we want to return is a list that contains only one thing, and that's the empty set. Right? Because this power set is supposed to be a list of lists, and if there's nothing to take a subset of, well, all you can get is the empty set, so you get one thing in your list. All right. Now what if it's bigger than 0? So how can we use recursion here? No ideas? Well, so if I look at all of these things that I drew here, some of them include the number 1, and some of them don't. How many include the number 1? 4 of them. How many don't include the number 1? 4 of them. Okay. So, I don't know. To me, that suggests that if I want all the power sets of this whole set, what I do is I take all the power sets, or I take the power set of 2 and 3, which is all the sets that I can make using 2 and 3, and then I can add 1 to each of those sets, or I can leave 1 out. And that'll give me all the sets that I can make out of 1, 2, and 3. So let's see how to implement that in code. So this says, actually, the first thing we should do is just compute the power set of a smaller set. So let's take and save it as the power set of A, ignoring the first element. So A from 1 up until the end. And so now we would like to turn this into something that's twice as big, where the first part maybe doesn't contain A at 0, and the second part does contain A at 0. And that's pretty easy to do. So let's say SS with A0 is equal to A at 0 plus X for X in SS. Okay. So SS is a list of lists. So that means X, which takes on each of these things, is a list. And so what I want to do is take A0 and then append it to that list, add those two things together. So this will give me all of the things that are in SS, but now they have A added onto them. And what I want to return is SS plus SS with A0. All right, let's try it. So let's say A equals 1, 2, 3, power set of A. So there we go. The empty set, the set that contains only 3, the set that contains only 2, the set that contains 2, 3, 1, 1, 3, 1, 2, and 1, 2, 3. If A is power set of A's there, we can, the length of the power set of A is 1024 if A has 10 elements. So we can do a quick check. What we said that the power set should have size 2 to the n, and indeed 2 to the 10 is 1024. Okay, so power sets, who cares? What are they good for? Well, it turns out that there's a lot of problems. There's a lot of problems that can be solved just by trying all of the possible potential solutions. And one of those problems, which is a famous one, and actually in many cases there's no better way to solve these problems than that. A famous one of those is the so-called subset sum problem, which says, I give you a list of numbers, A, and I ask you to find if there's a subset of those numbers which add up to some target value t. Okay. So think of it this way. So sometimes this is called the thief's problem. So I break into a gold store and or something where there's big chunks of raw gold or raw diamonds or something. I have a knapsack. The knapsack can I don't know, the straps break if the weight exceeds exactly some weight t. And so what I want to do is put pieces of gold into that knapsack until I have exactly t. And I don't have a saw with me, so I can't put half a piece of gold. I can't cut it in half. So what I'd like is to fill it so that it's exactly full, no extra space left. But if I put too much and go over, then I'll break the straps on the knapsack and I won't be able to take anything with me. So that's the subset sum problem. You give it a list of numbers and you ask it, with those numbers, can you make this this value t? And it's actually easy to solve using power sets. So you just say, let's take all the subsets of these numbers, A. So we'll say the power set is the power set of A. And now we're interested in those ones that, that add up to t. So we want to return x for x in the power set if the sum of x is equal to t. And in fact, let's be super slick about it. One-liner. So this is, subset sum is what's known as an NP-hard problem. Anybody heard of NP hardness, NP completeness? You will before you're through your studies. It sort of means these are the hardest problems that we know of, and here we're solving one using one line of code. You'll be suitably impressed by the time you graduate, even if you aren't now. And so let's say A equals range 10. And I want to know, so here's my set A. I want to know, can I make the number 33 out of A? So let's try subset sum A 33. Indeed, there are lots of ways to make 33 out of A, I think. Yeah. So let's try something harder. 34. Let's try 42. A little bit less. And we can check. So these are solutions to this thing that you can get from this particular range of elements. Okay. Let's make it a little bit harder for ourselves. Let's take A to be anybody know what the function is called that chooses a? Yeah, no, but there's one that actually you can specify how much you want. It doesn't matter. Okay, so somebody give me a target value for this set of numbers. All right, let's see if we can make 75. Subset sum x 75. Lots of ways to make 75. 6? Nope, can't make 6. 123. No ways to make that. How about 77? Lots of ways to make that. It's all the ways you can make 75, and then you just take this extra 2. So there you go. You give me this any set of gold bars of any weights and any backpack, and I can use this to figure out if I can pack the backpack perfectly or not. Yeah. Yeah.
I noticed that it's like duplicates of all of them because there's 0.
Yeah. So so that means we'll get twice as many solutions as I think. So what's x? So I can say delete x at 0. Yeah. So now it's half as big, but still lots of solutions for a lot of these things. There you go. Okay, so we'll leave it at there for today. So hopefully you're convinced now that recursion is powerful. You can do lots with it, but there's a lot of things you also shouldn't do with it. Yep.
Just a quick question about the game assignment. Like,
Yep.
not this first one, let's do but the next one.
Mhm.
Does it have to be original content, or can we like